SwayamPrabha. Digital India. Educated India.
So, welcome once again to our discussion on resource economics, and basically we are discussing dynamic optimization, and in our previous class we are basically trying to understand how the process of optimum control is involved in the context of dynamic optimization, right. We derived three conditions from our Lagrangian expression, and the Lagrangian expression was basically derived from the objective functional, where we said that we have a resource and we are trying to derive some kind of benefits from this resource, and the benefits are of two types: flow benefit and the scrap value, right, scrap value. And then from that we derive the Lagrangian expression, and optimizing that Lagrangian function we derive three conditions, and those three conditions we said that these three conditions are called maximum principle, and the entire process is known as dynamic the optimum control. The entire process is known as optimum control. Then at last we were discussing one particular example. What is that basically? So, this is dynamic optimization. So, let us assume we hold a stock of a company. So, if we hold the stock of a company, then there are two benefits. There are two benefits. What are those? Number one, flow benefit, and this flow benefit is actually given by that V function, okay, V function. And then secondly, there is another benefit, which is flow benefit denoted by V, and that basically indicates dividend from the stock, that is flow. So, if you buy and hold the stock of a company, the company will pay you dividend as long as you hold the stock, that is called flow benefit. And at the end, when you sell the stock to someone else, then what you will get, the other benefit, which is called future value of the stock, and that is basically denoted by lambda t into f dot. And we said that the h function, we defined one function h equals to v plus lambda t f dot. So, this is flow benefit and this is called future value of the stock. So, some kind of stock benefit. Now, the stock benefit is realized at one point of time, but this is a stream of benefits. So, that would be realized over a period of time. Now, suppose I want to convert this flow benefit into stock value. Stock, in a sense, this is when I say stock means at one point of time what would be the benefit. So, if we want to convert that a stream of benefit at present time, then basically we need to multiply this function with e to the power minus r t. That means a stream has to be discounted to get the present value of the flow benefit. So, basically then what we can write that if we multiply this equals to v function e to the power minus r t plus lambda t into f dot. So, I have simply converted the stream or flow benefit at one point of time by discounting that, and if we do so, then this h function is known as Hamiltonian function, and that is called present value Hamiltonian. This is called present value Hamiltonian. Present value Hamiltonian. Okay. So, here we have converted flow benefit into one point of time. Okay. So, here basically flow benefit is converted into stock benefit. By stock I mean the benefit which is realized at present. Okay. Instead of getting the benefit over a period of time, I want to get it now. So, then obviously you need to convert this v function into present time by discounting it, where r is the discount rate. So, you have to multiply that with e to the power minus r t. So, this is one type of Hamiltonian function. Similarly, what we can do, let us say I want to convert this future benefit which would be realized at one point of time into a stream like this, into a flow. So, what we need to do then? We need to multiply this by e to the power, let us say I am doing this, v I am keeping as it is, and this I am multiplying with e to the power r t into f dot. Okay, f dot, and that function is basically what I am saying. So, this is basically then I am doing this is let us say h bar I am writing, okay, and this h bar is known as current value Hamiltonian. Now, do not get confused with the current and present, though the English meaning of present and current both are same. Here these are two different functions, we need to understand conceptually. Here I have converted the stock into a flow and then I am adding it. Basically the idea is, in this h function I have two types of benefit, one is flow, another one is stock. Now, when you are adding, we can convert the flow into stock or stock into flow by multiplying either e to the power minus r t or e to the power r t, right. That is the idea. Okay, that is the idea. Now, let us assume that what we can write. So, this is basically from here in the next page what I will write, h bar equals to this I have written. Now, let us assume lambda t into e to the power r t e to the power r t equals to rho t, okay, rho t. So, this rho t is known as current value of the co-state variable. Now, if you look at this rho t is how we are getting lambda t multiplied by e to the power r t. Now, lambda t, if you go back and see, this Lagrangian multiplier lambda t is basically we have defined the co-state variable because it was attached with the state variable x t. So, the interpretation of lambda t is basically the co-state variable, or we have also defined lambda t is the marginal benefit, marginal preservation benefit. If you preserve the state variable, the stock, then what is the benefit? Since lambda t was attached with the state variable x t, that is why this lambda t is known as co-state variable. Since we are multiplying this co-state variable with e to the power r t, we said that rho t is basically the current value of the co-state variable. So, from here what we can say that means lambda t basically equals to rho t into e to the power minus r t into e to the power minus r t. Okay. So, if you from here what I can say that rho dot t dot means differentiating with respect to t, rho dot t equals to then what I will write, sorry, lambda dot t would be equals to rho dot t into e to the power minus r t minus r into rho t into e to the power minus r t. Okay. Now, if you both side multiply it by e to the power r t, then what you will get lambda t into e to the power r t equals to then rho dot t minus r into rho t. Okay. How we are getting it? Multiplying both side by e to the power r t. Multiplying both sides with e to the power r t. So, from here what we can get rho dot t equals to lambda dot t e to the power r t plus r into rho t. So, this is basically a condition which would be used later on. So far why we are discussing this mathematical procedure? Because this results, this would be useful when we actually talk about the optimum extraction of a non-renewable or renewable resource. That means, while deriving the optimum extraction path, these small mathematical conditions what we are deriving, those would be useful, right? Those would be useful. Now, previously we have defined the h function, particularly the present value Hamiltonian equals to this. So, present value Hamiltonian, if we differentiate, that means when you are trying to maximize the flow and stock, these two benefit, what we have to do actually, we need to differentiate this Hamiltonian with respect to your decision variable, which is nothing but y t, very simple, and set it equals to 0. Okay. So, this present value Hamiltonian is nothing but representing two types of benefits that we can actually get from a resource or from an asset. One is flow, another one is stock benefit, and here we have just made some changes, some modification to bring both the benefits into same platform, that is all, either flow into stock or stock into flow. So, here it is flow into stock. If we derive, then we will get the present value Hamiltonian, and if we try to maximize, then maximizing total benefit so flow plus stock requires what is required? Del H del YT equals to 0, that is all. Now, if you differentiate that H function, what you will get? You will get del V dot del YT into e to the power minus RT plus lambda t into del F dot del YT, because YT was there in V function, YT was there in this F function also. So, differentiating Hamiltonian with respect to YT means you have to differentiate this. Okay. And we also know that lambda t is basically equals to minus delta H dot delta xt. So, this we have derived earlier, one of the conditions from our maximum principles. Okay. So, this is what we got. So, that means from here, if we differentiate this, sorry, delta lambda dot t equals to minus del H dot del xt. Okay. So, this is we got earlier, and then multiplying this with e to the power RT will give you minus delta del xt into e to the power RT. Okay, e to the power RT. And this lambda dot t into e to the power RT is nothing but from here what we can get, rho dot t minus r into rho t. So, this we can write rho dot t minus r into rho t equals to, then when you multiply this with respect to multiply with e to the power RT, then basically you will get the current value Hamiltonian, which is nothing but minus del H bar del xt. Okay, that is what we got. So, from here what we can write, that rho dot t equals to, so from here what we can write, rho dot t equals to r into rho t minus del H bar del x t. So, this condition also we have to keep in mind, this will also be useful. Okay. So, this will also be useful. So, this condition you have to sometimes you have to go back this how lambda dot t equals to del H dot del xt, that we have defined earlier. Okay, thus we have defined earlier. Now, using these conditions, what we will do, we will now try to understand how these conditions are useful in the context of a non-renewable resource extraction. Let us now assume we have a stock of non-renewable resource from which let us say rate of extraction is YT and price equals to PT, price per unit of that. So, this implies, the instantaneous revenue from the resource extraction is equals to PT into YT, very simple. Let us also assume cost of extraction C is actually a function of, it should be a function of your rate of extraction and this. Okay. So, obviously, cost of extraction is actually a function of the rate at which you are extracting and the stock what you are having. So, it is positive and it is negative. If you have more stock, cost of extraction is less. If you have rate of extraction is more, then cost is more. So, that is how we assume that del C del YT is positive and del C del XT is actually negative. Okay. So, net revenue or net benefit equals to then PT into YT minus C of YT to XT. This is the net revenue. Okay. And this is something the resource owner is trying to maximize over a period of time. So, that means the objective of the resource owner, would be maximize this entire benefit 0 to T, then PT into YT, okay, PT into YT minus C into C function, okay, e to the power minus RT dt. Okay. That is what the resource owner is trying to do. So, that means maximize this, and what is the control variable once again? The YT. And what is the constraint here? The constraint is basically x dot t, that means change in stock is negatively related with rate of extraction. Okay. This is called the dynamic constraint we talked about earlier. Dynamic constraint, and x0 equals to 0, x0 equals to, let us say, some stock, and xt is actually greater than equals to 0. So, that means we have some positive scrap value. So, this is the objective of the resource owner. Okay, this is the objective of the resource owner, right. So, what the resource owner has to do, the optimization actually requires, okay. So, what we will do to optimize this objective functional? The first step is to set up the Hamiltonian function, the current value Hamiltonian, and then what we will do? We will try to differentiate the current value Hamiltonian with respect to YT and set it equals to 0. So, that means optimization requires two things: setting up current value Hamiltonian and then number 2, differentiating current value Hamiltonian, which is, let us say, HC or H bar. And second step is differentiating H bar with respect to YT and set it equals to 0. Okay. These are the two steps we need to follow. So, from this current value Hamiltonian would be simply the revenue minus the opportunity cost of extracting the resource today.